In this video for Chapter 18, we'll talk about electrophilic aromatic substitution reactions, including halogenations, nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation, and Clemmensen reduction. I've posted the slides for this video that you can print out ahead of time and fill in as you follow along. All electrophilic aromatic substitution, or EAS reactions, follow the same general mechanism. So let's go ahead and take a look at that mechanism. We'll start with our benzene ring. Now we know that a benzene ring contains 3 pi bonds. Now benzene rings, even though they contain pi bonds, are not the same as alkenes that contain pi bonds, and they don't undergo the same reactions that alkenes do. However, these pi bonds are capable of acting as nucleophiles, as we saw in the alkene addition reactions chapter. So when our benzene comes into contact with an electrophile, and an electrophile, we'll just use a generic one here, an electrophile often contains 2 parts. One part is slightly positive, the other is slightly negative. Now, our pi electrons are going to attack the slightly positive or positive part of our electrophile. So we're going to start our reaction arrow at the red pi electrons, and they're going to come and take the slightly positive portion of our electrophile, giving off the slightly negative portion. Now, this step in our mechanism is very slow. It's the rate determining step, and that's because what we're doing is temporarily getting rid of the aromaticity of the benzene ring. Now, after we have added the electrophile to the benzene ring, we're going to have our electrophile on one of the carbons that originally had our double bond. And we originally had an H here too. And the other carbon is going to get a positive charge. Now this positive charge is allylic. It's 1 bond away from a double bond here. So it is capable of participating in resonance. So these pi electrons can come over and we can create our first resonance structure. Putting the positive charge here. And then from here, we've created another resonance structure, an allylic positive charge, 1 bond away from this double bond. So the electrons will come over. And we create our third resonance structure. Now this is known as an rhenium ion. Which is a delocalized cation. So this will form fairly readily because we have resonance stabilization. Now, after we form our rhenium ion, the last step of our mechanism is going to be restoring the aromaticity of the compound. So what's going to happen is the slightly negative portion of our electrophile, which now has a full negative charge, is going to come in and it's going to remove the H that's on the same carbon as the electrophile. Then those electrons are going to go in the direction of the positive charge to restore that third pi electron. And now we have restored the aromaticity of the compound that has now included the electrophile as a substituent. Now this last step of the mechanism is extremely fast, and that's because we are restoring the aromaticity of the compound. So our EAS reactions are basically adding different electrophiles to our benzene ring. So in halogenation, we're adding halogens. In nitration, we're adding a nitro group. Sulfonation, we're adding a sulfonyl group. Alkylation will add some sort of R group. And acylation, we're adding an R group that has a carbonyl attached. So this whole group here is called an acyl group. So in the next few slides, we'll take a look at each one of these reactions. For the halogenation reactions, the two most common halogens to be added to a benzene ring are chlorine and bromine. So in these reactions, we will be adding chlorine and bromine, and it will also involve a Lewis acid catalyst. So we either use ferric chloride or iron trichloride, or we can use ferric bromide or iron tribromide. Another common Lewis acid catalyst can be aluminum chloride or aluminum bromide. Now, sometimes the temperatures of these reactions will be included. These are less important for you to remember. The most important things that you want to know are the fact that we need to react a benzene ring with chlorine as well as this Lewis acid or aluminum chloride. But ultimately, we're going to follow the same or similar EAS mechanism that we just saw to add the chlorine to the benzene ring. We'll go ahead and take a look at the mechanism on the next slide. Now, for the electrophilic aromatic substitution reactions, the mechanisms are broken up into two main steps. The first step is the formation of the electrophile. Now, unlike alkenes, benzene rings need to react with extremely strong electrophiles. Since we're temporarily destroying aromaticity, it needs to have some incentive to have a reaction take place. So in our first step for halogenation, and we'll go ahead and do the halogenation, we'll use bromine. So we have Br2. Our bromines each have 3 sets of lone pairs. Now we will use iron tribromide, which is going to serve as our Lewis acid. Now Lewis acid is an electron donor. The iron has space to accept electrons. So what's going to happen is with our Br2, there's going to be a temporary shift in electrons. So this is a nonpolar molecule, but remember it has London dispersion forces. So at any given moment, the shared electrons can all shift towards one of the bromine atoms. So we'll go ahead and say that at this moment, the electrons are going to shift towards the bromine on the right, which is going to give it a slightly negative charge. The other one will get a slightly positive charge. So now this bromine is going to go and it's going to donate its electrons to iron. Now, at this point, we are going to form a complex with the Br2 and the iron tribromide. Now, after this, we're going to have a negative formal charge on iron. And remember that metals do not like to have negative formal charges, so it's going to want to try and get rid of some of its electrons. We're also going to have a positive charge on this middle bromine here, which halogens don't like to have positive charges because they like to be surrounded by a lot of electrons. A positive charge means that it lacks the number of electrons that it wants. So this is going to serve as our super strong electrophile. Now for the next step, step 2, our benzene ring can attack our electrophile. So the pi electrons are going to go and take the bromine at the end of this complex. That's going to break the bond between the two bromines and give the electrons to the middle bromine. That's going to get rid of the negative charge for that particular bromine. Now, after this attack, we're going to have the bromine on one of the carbons of the benzene ring, and we'll have a positive charge on the other one. So we're forming our first iridium ion resonance structure. Now we know that we can have 3 resonance structures exist for this iridium ion. These pi electrons can come over. We'll form our first resonance structure. Sorry, our second resonance structure. And then again, these ones can come over to form our third. Then our last step is going to be restoring the aromaticity of the compound. Now we still have our Lewis acid with a negative charge on iron. Now iron is going to want to get rid of electrons. So what it's going to do is it's going to kick off this bromine along with its electrons. And they're going to come over and take the H on the carbon containing our electrophile. Then the electrons will go in the direction of the positive charge to restore the aromaticity. So we've formed our benzene ring with the bromine substituent. We're also going to get HBr as a product, and we're going to regenerate our Lewis acid catalyst, which can then continue on in the reaction. Our next reaction is nitration, which involves installing a nitro group on the benzene ring. Now, as far as the mechanism for this reaction, the main thing that's going to vary from the halogenation mechanism that we just saw is that first step, the formation of the electrophile. So this reaction involves nitric acid and sulfuric acid in order to perform the nitration reaction. So let's go ahead and take a look at that first step, that formation of the electrophile. Now, sulfuric acid and nitric acid are two of the 6 strong acids. But in this step, one of the acids is actually going to act as a base. So I'm going to go ahead and take our nitric acid and draw it out. And this is our structure for nitric acid. Now, sulfuric acid has a pKa of about -9. Nitric acid has a pKa of -1.4. So in a reaction with sulfuric acid and nitric acid, the sulfuric acid is the strongest. It's going to act as the acid. And our nitric acid, this is one of the few times where it's actually going to be acting as a base. So what's going to happen is the oxygen that holds the acidic proton has 2 sets of lone pairs. One of those lone pairs is going to go and take one of the acidic H's from our sulfuric acid. Now at this point, we will have our oxygen with 2 H's and a positive charge. Essentially what we're doing is we have turned our OH from a bad leaving group into H2O, which is a better leaving group. So now this is going to act as a leaving group. So now our negatively charged oxygen is going to go and it's going to donate its electrons to form a double bond between the nitrogen and itself. That's going to kick off the leaving group as water. And the result of this step is our super strong electrophile known as a nitronium ion. So after we formed our nitronium ion, now it can react with a benzene ring. The benzene will go and attack the nitrogen and kick up the electrons onto either one of the oxygen atoms. And then we will continue with the EAS mechanism. Okay, so the rest of this mechanism is going to be exactly the same as what we've seen twice before. The only thing that differed was this first step, this electrophile formation. So our next reaction is sulfonation, and sulfonation involves installing a sulfonyl group on the benzene ring, which is this group here, SO3H. Now there's two main ways that the reagents for this reaction can be written. It can either be written as sulfur trioxide with sulfuric acid, or, and this is more common, we're going to be seeing the reaction written as fuming H2SO4. On the next slide, we'll see why either one of these is an appropriate way to write the reagents. So sulfuric acid is actually capable of reacting with itself. So if you have a large concentration of sulfuric acid, 2 moles of that sulfuric acid can react with itself to produce the sulfur trioxide plus hydronium plus HSO4 minus. Now the electrophile in this reaction is the sulfur trioxide. So that's why we can write it in either one of those ways. So you can either write it as sulfur trioxide with the sulfuric acid, or the fuming H2SO4 just means concentrated hot sulfuric acid. So either one of those is still going to produce the sulfur trioxide. Now this is our electrophile because of its structure. The sulfur trioxide has a sulfur that is double bound to 3 oxygens. So the sulfur atom in the middle has a very large partial positive charge, which makes it attractive to nucleophiles. So when our benzene ring comes into contact with our strong electrophile, it can attack our sulfur atom and we can kick the electrons up onto any of the oxygens. Doesn't matter which one. Then we produce our rhenium ion, which we know can participate in resonance. Now I'm not going to draw all of the resonance structures now, but I'm going to move on to the second step of our electrophilic aromatic substitution, which is restoring the aromaticity. So the water that is floating around in the solution can come in and take an H and give the electrons toward the positive charge. Now, our sulfonyl group is SO3H, so we have one more step in this mechanism, which is adding an H to this negatively charged oxygen here. So the hydronium that we just produced is going to come in and serve as our proton source. We will protonate that oxygen, and we will generate our sulfonyl group. Now, after we protonate this oxygen, we're also left with water as a product. Now, this reaction is highly sensitive to water. So any addition of water or dilute sulfuric acid will actually remove the sulfonyl group. And that's because any addition of a product is going to push the equilibrium back to the reactants. So we're going to end up with just a benzene ring. So this is actually going to be very important when it comes to synthesis later on in this chapter. Our next reaction is the Friedel-Crafts alkylation, which will install an alkyl group on a benzene ring. Now, the electrophile in this reaction is actually a carbocation that can be formed from an alkyl halide, an alkene, or an alcohol. So we can actually use a wide range of reagents to install alkyl groups on the benzene ring. Now, all of these reactions are going to be run in the presence of Lewis acids. So that's all of these reagents here. They are serving as Lewis acids that will help with carbocation formation. So we learned last semester that carbocations don't form very easily. They're often the rate determining steps in different types of reactions. So these Lewis acids are there to really just promote that carbocation formation. So let's go ahead and take a look at the mechanism for Friedel-Crafts, and we will be using an alkyl halide and a Lewis acid. So step 1, again, is our electrophile formation. We'll go ahead and use this alkyl halide here, and we'll use aluminum chloride as our Lewis acid. So similar as what we saw with the halogenation, the lone pairs on the chlorine are going to go and attack the aluminum of the aluminum chloride. So again, this is our Lewis acid, which is capable of accepting electron pairs. Now, also similar to the halogenation, we form a complex, where we have a negative charge on aluminum. So again, we have a metal with a negative charge and a positive charge on chlorine. So again, halogens do not like to have positive charges. So that is going to really drive the carbocation formation. Because chlorine does not want to have this positive charge, it's actually going to pull the electrons away from the carbon atom that it's attached to. So we're going to have it leave, and we form a secondary carbocation. Plus our Lewis acid, which still has one additional chlorine and a negative charge on the aluminum. So once we form our carbocation, now the benzene ring can react with it. It will go and attack the carbon with the positive charge. We form our rhenium ion, which we know can participate in resonance. And again, I'm not going to draw all the resonance structures. Then our last step is going to be restoring the aromaticity. So this is where our Lewis acid complex comes in. So we still have this negative charge on aluminum, and it wants to get rid of that negative charge. So it's going to kick off this chlorine as well as the shared electrons. Those electrons will go, take the hydrogen, the electrons will go in the direction of the positive charge. We will restore the aromaticity of the compound. And we are also generating our Lewis acid again, which can continue on in the reaction, as well as HCl. Now, because the Friedel-Crafts alkylation involves a carbocation, there are a few limitations that we have to take into account when we're considering the different types of alkyl groups we can install on the benzene ring. So for instance, if we wanted to install a straight chain alkyl group using this alkyl halide to create a benzene ring with a 3-carbon straight chain, this would be our goal product, we have to think about the mechanism. So for this mechanism, we would take the alkyl halide, react it with our Lewis acid, aluminum chloride, and form our Lewis acid complex with a negative charge on aluminum, positive charge on chlorine. Now, once this leaves, we would generate a primary carbocation. Now, we learned last semester that carbocations can undergo rearrangements. So we can actually have a hydride shift occur. To form a much more stable secondary carbocation. So the problem with using a reagent like this is that it can undergo rearrangement. In the end, you would end up with two different types of products. You would have one with the rearranged carbocation, as well as some product with the straight chain. So the problem with this is you would get a mixture of products. So one thing to keep in mind with Friedel-Crafts alkylation. The second limitation is that yields are poor when the molecule contains a strong or moderate electron withdrawing group. And we'll talk about this a little bit more in the next video, but a nitro group is considered a strong electron withdrawing group. And what that means is it's pulling the electron density of the benzene ring more towards itself. Now, the carbocation electrophile that forms in Friedel-Crafts doesn't form very quickly and is not that stable. So it's not as strong of an electrophile as you would see in the other reactions. So a weaker electrophile combined with a less reactive benzene ring is going to make the reaction not very efficient, and it results in very poor yields. So we'll talk about this a little bit more in the next video, but just something to keep in mind as one of the limitations for Friedel-Crafts. For our third limitation is you cannot use vinyl or aryl halides as reagents. So this is considered an aryl halide where you have a halogen directly connected to a benzene ring. This is a vinyl halide where you have a halogen directly connected to the carbon of an alkene. Now these carbocations that would form if this were to occur would be highly, highly unstable. So if they're highly unstable carbocations, they will not form in the first place. So for the most part, we are looking for halogens attached to sp3 hybridized carbons in order to form stable carbocations. And our last limitation of Friedel-Crafts is that polyalkylations can occur. So that means that we can actually add a number of alkyl groups to our benzene ring. This is going to have to do with the fact that alkyl groups are what's known as activating groups. They're going to make the benzene ring a lot more reactive. So once we form our initial alkylated benzene ring, these pi electrons actually want to react even faster than a normal benzene ring. And so they will continue to react with whatever carbocations are in the solution. And as a result, you can get benzene rings with multiple alkyl groups attached. Again, we'll refer to this again in our next video, but it has to do with the fact that alkyl groups are slightly activating. And this brings us to our last reaction, the Friedel-Crafts acylation, which is very much related to the alkylation. But instead of attaching an R group to the benzene ring, we are attaching an acyl group, which is a carbonyl with any sort of R group attached to it. So this can be a long carbon chain if we would like it to be. So let's go ahead and take a look at the mechanism for the Friedel-Crafts acylation. And again, we'll break it down into two steps. So the first step is going to be the formation of our electrophile. Now this reaction also runs in the presence of a Lewis acid catalyst. And we'll use aluminum chloride here. So as we've seen with the previous reactions, we're going to have the chlorine of the acyl chloride come in and attack the Lewis acid. Now we'll form a complex where we have a negative formal charge on aluminum, a positive formal charge on the chlorine. Then we're going to see the chlorine leave and break the bond between itself and the carbon of the carbonyl. So this is going to generate a very odd looking sort of intermediate where we have a positive charge on a carbon of a carbonyl. Now we were just talking about unstable carbocations on sp2 hybridized carbons, but this is actually a carbocation that can form pretty readily because it can have resonance occur. So we have a lone pair next to a positive charge. That means that these lone pair can come down and actually form a triple bond between the oxygen and the carbon. That's going to give the oxygen the positive charge. So this resonance can go back and forth. Now this intermediate is known as an acylium ion. And the acylium ion forms because it's stabilized by resonance. So once we have the acylium ion, this is going to be our super strong electrophile. And it can end up reacting with our benzene ring. Now for the most part, it's going to hang out in this resonance form because even though the positive charge is on oxygen, all of the atoms in this resonance structure have a full octet. So it's going to prefer, this is going to be our highest contributor to the resonance structure. So now our benzene is going to go and attack the carbon, which will kick the electrons up onto oxygen and get rid of that positive charge. We will form our uranium ion, which we know will undergo resonance. And then our last step to restore the aromaticity, we have our Lewis acid complex from our very first step. And we still have a negative charge on the aluminum. So the aluminum is going to kick off the chlorine and the electrons. The electrons are going to go and take the hydrogen, and they'll go in the direction of the positive charge. Then we restore the aromaticity of the compound, and we've installed our acyl group on the benzene ring. Now the Clemmensen reduction can be used with the Friedel-Crafts acylation to add alkyl groups while avoiding many of the issues with the Friedel-Crafts alkylation. So we saw in our first limitation of the Friedel-Crafts alkylation that if this were our goal product, we would run into several issues with carbocation rearrangement. But let's see how we can use the Friedel-Crafts acylation with the Clemmensen reduction to actually make this goal product without a mixture of products. So we'd start with a benzene ring and we'd react it with a 1, 2, 3 carbon containing acyl group in the presence of a Lewis acid. So this would be our Friedel-Crafts acylation. So that would install our 3 carbon chain here. Next, we would treat this molecule with Clemmensen reduction conditions, including zinc, which is covered with a mixture of mercury, as well as hydrochloric acid and heat. So these reaction conditions are actually going to completely get rid of the carbonyl of the acyl group, and we're left with just a straight chain 3 carbon chain. So this is our Clemmensen reduction here. So these reaction conditions are very useful to get rid of carbonyls. Now, they really only reduce ketones and aldehydes. We're not going to see them reduce any other of the carbonyl containing functional groups. But it's a useful reaction that we'll see in later chapters as well. Now we do have to be careful with the Clemmensen reduction conditions because similar conditions also reduce nitro groups to amines. So NO2 is our nitro group. We can actually convert a nitro into NH2, which is an amino group, by using zinc and hydrochloric acid followed by sodium hydroxide. So if you had a molecule with a nitro group on this benzene ring and you treated it with the Clemmensen reduction conditions, it's likely that this nitro group will be converted to an amine. So just a couple of things to watch out for when you are using the Clemmensen reduction condition.